Hello everyone, welcome to this new video. Okay, so in our previous videos we have discussed half part of module 4, that is stability analysis, right, of control system. So now this comes the second part of this module, which is a very important concept, and I need you all to please refer the full video, okay, without skipping any part of the video, in order to understand this concept root locus thoroughly. Okay, this is a very important concept, and I would be trying my best to give you the detailed explanation about this concept. Okay, so let's start with this concept called as root locus. Okay, so now what is this root locus, how the graphs in this case are constructed, how are the mathematical steps, what are the rules to construct the root locus, with all the necessary steps we would be discussing now. First let us see what is root locus. Okay, again I'm telling you all, please don't skip any part, please refer the full video. Okay, so the root locus is a path of the roots of a characteristic equation traced out in S-plane as a system parameter which varies from 0 to infinity. Okay, so root locus is basically the path of the roots of the characteristic equation. So here we would be having one characteristic equation and the path of the roots. So for example, in a characteristic equation, if we try to find the roots of that characteristic equation, that particular roots is represented in the graphs, okay, in the forms of zeros and poles. Okay, so in the graph the poles are represented like this and the zeros are represented like this. Okay, whenever we draw the graph, you need to remember this first. Okay, traced out in S plane. Okay, S plane means left half of the what to say, negative axis. Okay, the right half is the positive side and the left half is the S plane. Basically you can see the second quadrant of the graph. Okay, as a system parameter which varies from 0 to infinity. Okay, the poles value of the poles vary from 0 to infinity. Okay, so now let's see what are the angle and magnitude conditions. It helps to construct the root loci angle. We know that 1 plus g of s into h of s is equal to 0. This is represented as a characteristic equation. Therefore, we can say g of s into h of s is equal to minus 1. Therefore, we can represent the angle as g of s into h of s is equal to angle of minus 1, that is equal to plus or minus 180 degree of 2k minus 1, where k varies from 1, 2, 3, etc. Okay. So this was all about the basic definition of this root locus. So now comes the very important part which you should not be skipping, and also this is very important, that is rules of construction of this root locus. Okay, so now how to construct this root locus in the graph. Okay, before constructing the root locus in a particular S plane or the graph, we need to be knowing some certain rules. Okay, that is, rule number 1 says that root locus is always symmetric with respect to the real axis. Okay, that means in the root locus always lies in the real axis only, that is from minus infinity to plus infinity. Wherever it is, the root locus always lies on the real axis. Okay, which is tilted with some certain angle that we will be seeing it later. It is not symmetric to imaginary axis. So in this root locus, while constructing the graph, we would be having two axes, that is, one is real axis which is perpendicular like this, it is represented as like this. This is the real axis part and this is the imaginary axis part. Okay, it is represented like this in the graph, where this vertical line represents the imaginary axis of a plot and this horizontal line represents the real axis of the plot, which varies from minus infinity to infinity with an origin, and here also minus I infinity to plus I infinity. Okay, so this was the first rule. The second rule says that we need to identify the number of loci. Okay, loci means number of root locus. The plural of locus is loci. How to identify the number of loci or the number of curves which is formed from the graph. Okay, we have a certain set of to find the number of loci. Rule 2 says that it is max of p comma z. Okay, so in a particular transfer function, first we need to be writing the transfer function, and first we need to be writing the number of poles and number of zeros present in that transfer function by checking the numerator and denominator terms. Okay, then max of p comma z. Say for example, in a particular transfer function we have number of poles as 3 and number of zeros as 2. Maximum of p comma z is we can say that max of p comma z means which is the having the maximum value, that is poles are having the maximum value in this case, which I am taking the example now. So the total number of loci is max of p comma z. So therefore our total number of loci in this example is 3. Okay, since max of p comma z where poles are greater than zeros, so that's why we are taking this value as total number of loci. Okay, so for this also we are having few of the sub cases which are very important. Okay, in rule 2 we are having 3 cases, that is case 1, if poles are greater than zeros. Okay, for a particular transfer function, if there are more number of poles than more number of zeros, we have few set of rules, that is number of branches are equal to number of open loop poles. Branches will always start from each of the open loop poles. Okay, the branches of the root loci will always start from each of the open loop poles. It will always start diverting from the open loop poles. Out of p number of branches, z number of branches will terminate at the location of the open loop zeros, and p minus z number of branches will approach to infinity. So now what does this statement mean? It means that in a particular, if we take an example of this only, that is poles, we have 3 poles and 2 zeros. Okay, this says that out of p number of branches, z number of branches will terminate at the location of open loop zeros. For example, that is, since we have 3 poles here and 2 zeros, the 2 out of 3 poles would be approaching to 0, that is it will terminate at 2 of the zeros in the plot, and the one more pole which is left out, that would be approaching to infinity. Okay, if we take one more example, if in a particular plot, if we have 4 poles and 2 zeros, 2 poles here would be terminating at 2 of the zeros in the plot, and rest of the 2 plot will be approaching towards infinity. Okay, that would be seeing thoroughly while we draw the graphs of some of the root locus problems. Okay, when we solve it. So this is that condition. Case 2 says that if z is greater than p number of branches will start from open loop poles, while z minus p number of branches will originate from infinity and terminate to open loop zeros. Okay, that is, it would be originating from infinity whenever there are more number of zeros, and it would be terminating to the same, that is open loop zeros. Okay, so case 3 says that if z is equal to p, separate branch will start from open loop pole and end at zeros. No branch will start and end at infinity. That is, if there are equal number of zeros and equal number of poles, that all the branches would be starting from open loop poles and it would be terminating at zeros. So no what to say, root locus plots would be approaching towards infinity. Okay, whenever there are equal number of poles and zeros. Okay, so this is all about rule 2. Now let's discuss what is rule 3. So this is the rule 3. The rule 3 says that total number of asymptotes, this is asymptotes. Okay, or we can call them as a straight lines. Okay, total number of straight lines, where straight lines, that is asymptotes, is equal to total number of poles minus total number of zeros. Okay, note the branches which are approaching to infinity will do so along the straight line called asymptotes of root locus. Okay, so now what are these asymptotes or straight lines of root locus? Okay, that is the branches which are approaching to infinity when we have a greater number of poles in a plot. Some of them would be approaching to zeros and others would be approaching to infinity, right? And which the branches of the root locus which are approaching to infinity will do so along the straight line called asymptotes. Okay, so in the root locus graph we would be having we would be constructing few of the straight lines in order to set the directions of the root locus branches, in which direction it is approaching to infinity. Okay, for that case we are drawing these straight lines and they are called as asymptotes. Okay, so now how to calculate the number of asymptotes in a particular problem? And we can calculate number of asymptotes by total number of poles minus total number of zeros. Okay, that would be giving our asymptotes or number of straight lines which we are having in the plot. Okay, so now let's see what is rule number 4. Rule number 4 is angle of asymptotes. Okay, angle made by those straight lines. Okay, so now what are those angle made by those straight lines and how it is calculated? We have a formula for that, that is theta is equal to 2q plus 1 into 180 degree divided by number of poles minus number of zeros, or we can simply write it as p minus z, where the value of q is from 0, it goes from 0, 1, 2 up to p minus z minus 1. Okay, so now what is this p minus z minus 1? Let's see this with an example. Okay, so for example, if we are having number of poles as 4 and number of zeros as 1. Okay, so now in order to calculate the value of q, we need to be calculating how many angles does the angle of asymptotes make. Okay, for example, let's first try to see what are the total number of asymptotes in this case. That is total number of poles minus total number of zeros. So total number of asymptotes which are we getting it here, it's 3. So if we are getting 3 asymptotes, we must get 3 angles for those asymptotes. Okay, so for that case the value of q would be ranging from 0, 1, p minus z minus 1, that is 4 minus 1 minus 1, that is equal to 2. So 0, 1, 2. So if we have 3 different values of q, it's definitely from the logic we can say that if we substitute one by one the values of q as 0, 1, 2, we would be getting 3 angle of asymptotes. Our goal is how many number of asymptotes are there, that many angle of asymptotes we need to calculate. Okay, so this is all about angle of asymptotes. Okay, that we would be seeing while we draw the graph. So rule 5, that is centroid of asymptotes. Okay, centroid means from that point we would be drawing the angle of asymptotes. Okay, so now how to calculate that centroid? From that particular point in the graph, okay, we would be calculating that centroid first, and from that point we are going to draw the angle of asymptotes. Okay, and those angle of asymptotes are made from the straight lines, that is number of asymptotes. So see how these three are interrelated. So now let's see what is the centroid of asymptotes. It is basically the location of asymptotes on the S-plane. Okay, all the asymptotes intersect the real axis at a common point known as centroid. Okay, and it is given as sigma. It is represented as sigma centroid, and its formula is summation of real part of poles minus summation of real part of zeros divided by number of poles minus number of zeros. Okay, so for a particular transfer function, we cannot say that the particular transfer function, the roots or the poles, so the poles or the zeros which you obtained is purely real in nature. Okay, it might be imaginary as well. Okay, so that's why in order to calculate this sigma, we need to be deriving this formula, that is if we have a number of poles as 2 or 3, the root obtained, in that root obtained we need to be summing up all the real part of poles, minus in the zeros obtained we need to be summing up all the real part of zeros if we have more number of zeros, divided by number of poles minus number of zeros. If we substitute the values and if we try to calculate sigma, we will be getting one value of sigma, and from that point of sigma we need to be drawing the angles of asymptotes which we have already calculated and kept. That angles of asymptotes are obtained through the number of asymptotes, that is number of straight lines. Okay, so these are all about 5 rules. Okay, hope you are listening to it very carefully. Okay, so let's see the rule 6 now, that is breakaway point. Root locus branches always leave breakaway point at an angle of 180 degree divided by n, where n is number of branches approaching the breakaway point. Okay, so this was all about the basic definition of the breakaway point. Okay, now let's see one important note, that is if there are two adjacently placed poles or zeros on the real axis and the section between them is a part of the root locus, then there exists minimum of one breakaway point between them adjacently placed zeros and poles. Okay, that is, so now what does this mean? That is between them is a part of root locus. So now how to say that this root locus or the root locus which we are obtaining, that the curve or the branch is a part of that root locus? How to calculate, how to check whether the section which we are drawing the root locus is a part of the root locus? So how can we calculate that? So now let's see how can we do that. Okay, so now look at this plot where I have drawn. I have drawn one rough plot here. Okay, in this, consider we have 4 poles in a particular transfer function. Okay, and that 4 poles are 0, minus 1, minus 2 and minus 3. And I have told you, right, the poles are represented like this by drawing a cross mark. Okay, so I have they have given 4 poles and the values of 4 poles are 0, minus 1, minus 2, minus 3. I have plotted them in series here. Okay, so now how to check the section between the part of root locus? Okay, how to check that is, from here we have one pole which is from 0, okay, and from -1 I've drawn one this right x-axis. From here, this pole, if we look to the right of the real axis, okay, if you look from this point to the right side of the real axis, okay, we can see that we are having only one pole, right? That is odd number of poles, okay. If from a particular pole, if you look from the right of that particular pole, the number of poles present is our odd number of poles, then we can say that the section between that pole to the nearer pole is a part of root locus, okay. So this section here is a part of root locus. Similarly, if we look the same from this point, that is from second pole, if you look it to the right side, we can see that we are having two poles, okay, that is even number of poles. If we have even number of poles, when we look from a particular pole in the right side of the plot, we can say that the section between that pole to the next pole is not a part of root locus, okay. That is, we can say that we cannot have any breakaway point in between this region, or we cannot have any branch which is going through this region, okay. That's why, since there are odd even number of poles when we look from this point, so this is not the part of root locus. Similarly, from this point, if you observe in the right side, we are having three poles, that is odd number of poles. So we can say that again this is a part of root locus, where in this regions the breakaway point can exist. Similarly, if we don't have any pole here, that is, we can consider that is minus infinity. From here, from minus infinity, if you observe again, we are having 4 poles, even number of poles. So we can say that from this pole up to minus infinity, this is completely not a part of root locus, okay. So we can say that whichever region is a part of root locus, from that region only we get the valid breakaway point. Also, the branches of root locus would be obtaining in this regions only, okay. So I hope you understood this concept very well. So now let's see how to determine the breakaway point, okay. So determining breakaway point, we have a few steps for that. Step 1, obtain the characteristic equation of the given transfer function. So they would be giving one transfer function. We should be obtaining the characteristic equation by simply writing the denominator of transfer function, that is 1 plus g of s into h of s is equal to 0, okay. After computing, then we would be getting the transfer function. That from that transfer function we need to be compute k polynomial, that is, from that transfer function obtained, bring k to one side and all the other terms to other side, in order to calculate the step 3, that is dk by ds, okay. That is determinant derivative of k with respect to s, which gives us the roots of s, okay. When we do dk by ds is equal to 0, we would be getting the roots of s, some of which may be a breakaway point, okay. That is, for example, if we have a if we get one polynomial equation after putting this dk by ds equal to 0 as s square plus 2s plus 2 equal to 0. So now we need to be finding its roots, okay. Let's consider that the roots which we have obtained is the values roughly I am writing, that is minus 1.5 and minus 0.5, okay. So now we need to be checking the breakaway point in this case, okay. These are the two breakaway points which we got, okay. But due to the example I have taken, we need to be checking which is the valid breakaway point. How to check that? So this minus 0.5, if it comes somewhere here, right, that is, it is a part of root locus, so this is a valid breakaway point. And this minus 1.5, the second root, comes over here, right, that is, but this region is not a part of root locus, so that's why we won't be having any breakaway point here. So this is invalid breakaway point and this is valid breakaway point. So this is just an example. With an example I've tried to explain, okay. That is, we can note that also we can determine whether the breakaway point is valid or invalid, that by whatever the roots we have obtained, we can substitute that roots in this k equation. That is, we have obtained this k equation from this characteristic equation, right. In this k equation we can substitute our values of roots here and check whether the breakaway point is valid or invalid. That is, we have that if k is positive after substituting s, that is the root in the above equation of k, then the breakaway point is said to be valid, okay. After substituting the roots, if we get our k value as positive, then the breakaway point is valid. Simply then, if the value of k is negative, if we substitute the roots, any one of the roots, then the breakaway point is invalid, okay. From that thing we can see the breakaway points whether they are valid or invalid. So now let's take rule number 7, angle of departure. Okay, so now what is this angle of departure in a particular root locus plot? Since branches of root locus always leaves from an open loop pole, it is required to know at what angle it departs from complex conjugate poles. Such angles are called as angles of departure. Okay, the general formula of the angles of departure are given as theta d is equal to 180 degree minus summation of theta p, that is angles made by poles, minus summation of theta z, that is angles made by zeros. This theta d is only valid when in the given transfer function, when we calculate the poles, if the poles which we are getting, if the poles which we get in the transfer function, if the poles are imaginary, then only this angle of departure rules comes to picture. Okay, we need to use this rule. If the poles which we obtain in the starting first step are not imaginary poles, then it's no need to require to find this angle of departure. Okay, so now let's see this angle of departure briefly when we solve one problem related to it. Okay, so now we have one final rule. Let's discuss that. Rule 8, that is intersection of root locus with imaginary axis. Okay, so now how to calculate this intersection of root locus with imaginary axis? We have again few steps for that. Step 1, obtain the characteristic equation of the transfer function, that is again the same thing, 1 plus u of s into h of s equal to 0. Step 2, construct the Routh array in terms of k. Okay, when we get the characteristic equation, construct the Routh array in terms of k. Then determine the marginal value KMR to obtain the row of zeros, that we already discussed how to determine that. Okay, then again from the row of zeros, above the row of zeros we would be having an auxiliary equation. Take that and put that a of s is equal to 0. Okay, substitute that auxiliary equation equal to 0. From that auxiliary equation, try to find the roots, that is the value of s. Okay, if the value of s is imaginary, if we get, for example, if it is of the form plus or minus j omega, okay, then if it is of the form s is equal to plus or minus j omega, after putting a of s is equal to 0, then that point, that is plus j omega and minus j omega, the values which we get is the intersection point of root locus on the imaginary axis. Okay, for example, we are drawing one root locus. For example, let's draw one simple root locus. Okay, this is one part of root locus, and here we have one breakaway point, and this breakaway point is moving, and it's moving like this with an angle, with some angle here, that is a centroid. From centroid we have marked few angles, right? And this is one simple root locus which is moving in this direction, and this meets to this imaginary axis. I've told you that this is the imaginary axis part, and here plus, that is plus j omega minus j omega, whatever we calculate, that is point of intersection, that this curve would be meeting this point, and then it would be approaching towards infinity. Okay, yeah, so this was all about the intersection of root locus with imaginary axis, and in this way we need to be drawing the root locus plots. So that's all for this session. Hope you understood all the rules very thoroughly. So please like, share, subscribe, and please watch the full video from starting to end, since this is a very important concept. I don't want anyone to skip any concept and tell that I didn't understand anything, because this is the basic. If you know this, we can solve all the problems very easily. Okay, so that's all. Like, share, subscribe. Please refer our playlists. Okay, it might be appearing on the right of your screen now, all the modules, all the concepts we have discussed. So please go through that, and also model paper we are going to provide it to you all. So please stay tuned to this channel. Like, share, subscribe guys. Thank you.